In this video, we're going to have a conceptual introduction to some of the issues associated with thinking about gravity. So in particular, I'm going to describe the way people think about gravity with Newton's universal law of gravity. This is as opposed to Einstein, and maybe even like weird, crazy stuff like quantum gravity. So these types of theories of gravity or ways of thinking about gravity are very, very different from Newton's universal law of gravity. Newton's universal law of gravity, I think, is the first sort of ultra successful predictive and simple theory of gravity or modeling of gravity. So what Newton's universal law of gravity does is it gives you a way to quantify. So it calculates gravitational force. So these are gravitational force vectors in all possible situations. So what's interesting to point out is its ubiquity. In all possible situations, this is the basic law, and it's very simple, it turns out. Thank you, Isaac Newton. So some things that Newton realized, or maybe Newton's guides or patterns for thinking about gravity and trying to build what's called a universal law for it. So here's what Newton thought. Gravity is only ever attractive. There is no repulsive gravity. It is strictly attractive. No repulsion, and also no like weird sideways stuff like shear forces or torsional stuff. There's no twisting because of gravity. It's only strictly attractive. And what's more is the force by gravity between two objects is going to be weaker if the objects are further apart, and also stronger if they're closer. So weaker if further apart, stronger if they're closer. And also the forces involved in a gravitational interaction are stronger if more matter, which is also known as mass, this is the quantification, if more matter is involved. So it's only ever attractive. There is a variation in the strength of forces. If the two objects are further apart, their attractive forces are weaker. If they're closer, they're stronger. And also, if there's more material involved, they're stronger. Okay, so it's interesting, like this one's easy to sort of see, like more massive things are heavier. So heavier refers to force, like weight, and mass refers to how much material is involved, how many atoms, how many protons, neutrons, and electrons. Yeah, and so if there are more protons, neutrons, and electrons, that thing is heavier. There is a stronger gravitational attraction. All right, but okay, so I'm gonna move on, and maybe one more thing is never turns off or shielded or hidden so never turns off and cannot be shielded or hidden. You can't hide gravity, can't hide from it either. And then another thing is, let's see, independent of motion. This is pretty cool. It turns out only dependent on separation. This fact right here, so one of Newton's thinkings is right here. This is kind of the same thing, right? It's weaker if further apart, and it's the same kind of thing as saying it's only dependent upon the separation of the objects involved. It doesn't matter how the objects are moving. Yeah. Okay, so these are some ideas about how Newton thought gravity would work. So, more concept. So this is going to get a little complicated. So let me warn you, it's about to become complicated, but the complication is based upon simple rules. So, but it is going to be complicated. So check this out. There's a tree. And in the tree are apples. So this is an apple tree. And the tree is on the earth here. Yeah, and so there's a famous story about Newton standing or sitting on a hillside somewhere, watching nature happen, thinking about stuff, and what Newton sees is a couple of apples in an apple tree, and also at the same time what Newton sees is the moon. So here's the moon, and Newton knows that the moon has this elliptical trajectory around the earth. So ellipse around earth. And this comes from astronomy. People do measurements and watch and track the path of the moon around the earth. But meanwhile, also, so here's the moon, and here are some apples. This little apple, or an apple a lot like it, falls out of the tree. So here it is, falling, right? Picking up speed, falling with an acceleration 9.8 meters per second squared. Right there. And so Newton watches this apple fall, also notes that the moon is doing this elliptical thing, and in Newton's mind, the moon and apple do what they do for the same reason. Whoops. This is the universality of gravity. That is, gravity is doing this to the apple, and gravity is doing the ellipse to the moon, in a sense. All right. So I told you it was going to get complicated. So let me explain why it's complicated. Gravity is more than the Earth doing this to the apple and the Earth doing this to the moon. So what sense is Earth doing this to the moon? It's actually kind of like this. So the moon, and here this is the center of mass of the Earth, and this is the center of mass of the moon. And the moon and the Earth are very far apart, but the amounts of material involved are huge. So they can have quite a large gravitational interaction. So these are forces. This right here is the force on the Earth by the moon because of gravity, right? So that's a force vector. And it's a force acting upon the Earth because of the moon, or I mean, by the moon because of gravity. Up here, this is the force on the moon by the Earth also because of gravity, right? And do you remember Newton's third law? For every action, there's an equal and opposite reaction, regardless of the interaction type. What this says is the force on the Earth by the moon because of gravity is equal to the opposite of the force on the moon by the Earth because of gravity. And so Newton's third law applies for gravity. It's still not complicated. Here's how it gets complicated. So the Earth is being pulled up towards the moon because of gravity, but the Earth is actually also being pulled up towards this apple. So regardless of how the apple is falling, it only depends on how far apart are the two objects. So the apple's center of mass is about here, the Earth's center of mass is here, so they are a separation distance of essentially the radius of the Earth, because this isn't very far above the surface of the Earth. And the amounts of mass involved, well, it's the mass of the entire Earth and the mass of the little apple. That's who's having a gravitational interaction. But the force on the apple by the Earth is towards the center of the Earth, right? These things are attracted center to center. And there's a force on the Earth by the apple. So there's two here. Here's another apple also being pulled down towards the Earth, and the Earth is also being pulled up towards that apple. Here's a third apple being pulled down towards the center of the Earth, and the center, the Earth is being pulled up towards that apple. Here's a person on the Earth being tugged down. That's the weight of the person. And the Earth is being tugged up towards the person, so they are snugged up against each other. The tree is probably pretty massive compared to the person, so let's make a bigger weight force vector. And the Earth is being tugged up towards that tree and every other tree on the planet. And the ocean, all the automobiles, all the buildings, the birds, the airplanes, they're all doing this thing with the Earth, right? So the Earth is really being tugged up towards all the stuff on its, near it, including the moon. And also, let's say the sun was way over here. The Earth is being tugged up towards the sun with a gigantic force, and the sun is being tugged down towards the Earth with a gigantic force. Complicated, right? So what's crazier than that, though, even more complicated, I was talking about all of the forces, or all of the interactions between the Earth and everything else. But it's way worse than that. The moon is attracted to this apple. And this apple is attracted to the moon. This apple is attracted to the moon. And the moon is attracted to that apple. And this apple is attracted to the moon. And this moon is attracted to that apple as well. This person is attracted to the moon. And the moon is attracted to that person. So we can talk about now the moon interacting with every other object. Right? We've already included the Earth. And you can see that it's getting complicated. But it's worse than that. This apple is weakly attracted to this apple. This apple is weakly attracted to this apple. This apple is weakly attracted to this apple. This person is weakly attracted to that apple. And this person is weakly attracted to this apple. And this person is weakly attracted to, this apple. Holy crap. Right? You can see that it's getting nuts. Also, all of the apples are attracted to the tree, and the tree is attracted to the apples. Right?